What if I told you that the most dangerous objects in the universe could fit inside a city, while something a million times larger might be completely harmless? In space, size doesn't determine power, density, gravity, and physics do. Welcome to the mind-bending reality where a teaspoon of matter can weigh as much as Mount Everest, where objects smaller than Manhattan can tear apart entire stars, and where the tiniest fragments of debris travel fast enough to obliterate spacecraft. Today, we're diving deep into the cosmic paradox where small truly means deadly. Let's start with something that sounds impossible. Imagine taking the entire mass of our sun, something so massive that over 1 million Earths could fit inside it, and crushing it down to the size of a city. Not a big city either, maybe just 10 to 20 kilometers across, smaller than Los Angeles or London. This isn't science fiction. These objects exist, and they're called neutron stars. They represent one of the most extreme states of matter in the universe, and they completely rewrite our understanding of what's possible in physics. When a massive star runs out of fuel, it can no longer support itself against its own gravity. The core collapses in a catastrophic event we call a supernova. For stars between about 8 and 20 solar masses, this collapse doesn't stop at a white dwarf. The gravity is so intense that electrons get forced into protons, creating neutrons. What you're left with is an object made almost entirely of neutrons packed together so tightly that a single teaspoon weighs about 1 billion tons. Let that sink in for a moment. 1 teaspoon. 1 billion tons. That's the weight of Mount Everest in a volume you could hold in your hand, if your hand could somehow survive the experience. The surface gravity of a neutron star is about 200 billion times stronger than Earth's. If you could stand on one, which you absolutely couldn't, you would be instantly flattened to a layer of atoms just a few hundred atoms thick. Any mountains on a neutron star can't be more than a few millimeters tall because gravity immediately crushes anything higher. The escape velocity is about 1/3 the speed of light. These objects spin incredibly fast, some completing hundreds of rotations per second. The fastest known pulsar, which is a type of neutron star, spins 716 times per second. Imagine something with more mass than our sun, compressed to the size of a city, spinning 716 times every single second. But neutron stars aren't just dense and fast. They have the strongest magnetic fields in the known universe. Some neutron stars, called magnetars, have magnetic fields 1,000 trillion times stronger than Earth's. These magnetic fields are so powerful, they can literally distort the atoms in your body from thousands of kilometers away. If a magnetar passed within 1,000 kilometers of Earth, it would strip the data from every credit card on the planet. If it got closer, it would pull the iron from your blood. The magnetic field itself would be fatal long before any other effect of the neutron star could harm you. When neutron stars have starquakes, cracks in their incredibly dense crust, they release more energy in 1/10 of a second than our sun produces in 100,000 years. In December 2004, a magnetar called SGR 1806-20, located 50,000 light-years away, released a burst of gamma rays that affected Earth's ionosphere. This was an object the size of Manhattan, halfway across the galaxy, and it still impacted our planet. If that same burst had occurred just 10 light-years away, it would have caused a mass extinction event on Earth. Now let's talk about something even stranger and more dangerous. Black holes. Not the supermassive monsters at the centers of galaxies, but stellar mass black holes formed from collapsed stars. A typical stellar black hole might contain 10 to 20 times the mass of our sun, but its event horizon, the point of no return, might only be 60 kilometers across. Some could be much smaller. The actual singularity, if it exists as a point, would have literally zero size but infinite density. This breaks mathematics as we know it. Black holes represent the ultimate expression of how size means nothing when gravity takes over. You could have a black hole with the mass of Earth that would be less than 2 centimeters across. It would be a tiny sphere sitting in your hand, except that it would immediately fall through your hand, through the floor, through the Earth, and settle at the planet's center while consuming everything around it. The gravitational pull at the event horizon of such an object would be so extreme that time itself would stop from the perspective of an outside observer. What makes black holes particularly dangerous isn't just their gravity, but what happens near them. As matter falls toward a black hole, it accelerates to tremendous speeds and heats up through friction, creating an accretion disk. This disk can reach temperatures of millions of degrees and emit intense radiation across the entire electromagnetic spectrum. The jets of energy shooting out from the poles of some black holes can extend for thousands of light years, carrying more energy than entire galaxies. And all of this is being powered by an object that might be smaller than a city. The tidal forces near a black hole are where things get truly horrific. As you approach a black hole, the difference in gravitational pull between your head and your feet becomes extreme. This is called spaghettification, and it's exactly what it sounds like. You would be stretched like a piece of spaghetti, with your body pulled into a long, thin strand. For a stellar mass black hole, this would happen before you even reached the event horizon. You would be torn apart at the atomic level, stretched into a stream of particles spiraling down into oblivion. But here's something that blows my mind. A black hole doesn't actually have to be massive to be dangerous. In fact, smaller black holes can be more dangerous in some ways. A small black hole has a much smaller event horizon, which means the tidal forces are more intense near the surface. If micro black holes exist, as some theories suggest, they could pass right through solid matter because they're so small. A micro black hole the mass of a mountain, but smaller than an atom, could punch through the Earth, and you'd never know it happened unless it happened to hit you directly. The universe might be full of primordial black holes created in the first moments after the Big Bang. These could range from microscopic to massive, and we have no idea where most of them are because black holes don't emit light. We can only detect them by their gravitational effects on nearby matter, or when they consume something and release radiation. There could be a small black hole drifting through our solar system right now, and we wouldn't know unless it passed close enough to something to make its presence known. Now let's shift gears and talk about something that seems trivial compared to neutron stars and black holes, but is actually an immediate and present danger. Space debris. We're talking about paint flecks, metal fragments, and tiny particles traveling at orbital velocities. In low Earth orbit, objects travel at about 17,500 miles per hour. At that speed, a paint fleck the size of a pencil eraser has the same kinetic energy as a bowling ball traveling at 60 miles per hour. It can punch right through a spacecraft's hull, through equipment, through a human body. In 1983, the Space Shuttle Challenger was hit by a paint chip just 0.2 millimeters across. It created a crater 2.4 millimeters deep in the windshield, requiring the window to be replaced. That's a microscopic speck of paint causing serious structural damage. There are currently millions of pieces of space debris orbiting Earth, ranging from dead satellites to fragments from collisions and explosions. Most of this debris is smaller than a softball, but all of it is traveling at velocities that make it deadly. The International Space Station has been hit by debris multiple times. The windows regularly need inspection and replacement due to impacts from tiny particles. The station has shielding specifically designed to protect against debris, using a Whipple shield that causes small objects to vaporize on impact with an outer layer, protecting the inner hull. But this only works for small debris. Anything larger than about 1 centimeter could cause catastrophic damage, and there's not much that can be done about it except track the debris and move the station out of the way. We're creating more debris all the time. Every satellite launch, every collision, every intentional destruction of a satellite creates thousands of new fragments. In 2009, an inactive Russian satellite collided with an active American communications satellite, creating over 2,000 trackable pieces of debris, and probably tens of thousands of smaller fragments. China's 2007 anti-satellite missile test created over 3,000 pieces of trackable debris that will remain in orbit for decades. We're essentially creating a minefield around our own planet, and these tiny fragments are the mines. The Kessler syndrome is a theoretical scenario where the density of objects in low Earth orbit becomes high enough that collisions between objects create a cascade effect. Each collision creates more debris, which causes more collisions, which creates more debris, until entire orbital shells become unusable due to the debris field. We're not there yet, but we're getting closer. Some scientists believe we may have already reached the point where certain orbits will naturally increase in debris density, even without new launches. Here's something that really puts the danger in perspective. During the Apollo missions, astronauts traveling to the moon passed through regions of space with micrometeorite particles. These are tiny fragments of asteroids and comets, usually smaller than a grain of sand, traveling at speeds up to 60,000 miles per hour. At those velocities, even a particle the size of a grain of sand has enough energy to penetrate a spacecraft hull. NASA calculated that there was about a 1 in 175 chance that Apollo spacecraft would suffer a critical micrometeorite impact during the mission. Those are not comforting odds when you're 250,000 miles from home. The danger isn't limited to human-made debris and micrometeorites. Cosmic rays are another tiny but dangerous phenomenon. These are high-energy particles, mostly protons, traveling at nearly the speed of light. A single cosmic ray particle contains an enormous amount of energy despite being just a single atomic nucleus. When cosmic rays hit spacecraft electronics, they can cause bit flips in computer memory, corrupting data or causing malfunctions. In the human body, cosmic rays can damage DNA, increasing cancer risk. On long-duration space missions, especially beyond Earth's protective magnetic field, cosmic ray exposure is one of the most serious health risks astronauts face. Some cosmic rays have truly mind-boggling energies. In 1991, a cosmic ray particle was detected with an energy of about 300 million trillion electron volts. This single particle, probably a proton, had about the same kinetic energy as a baseball traveling at 60 miles per hour. One particle, one proton, with the energy of a baseball. We still don't fully understand where ultra-high energy cosmic rays come from or how they achieve such incredible energies. Let's talk about gamma-ray bursts, one of the most energetic events in the universe. These bursts release more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. They're thought to be caused by the collapse of massive stars into black holes or by collisions between neutron stars. The burst itself is highly directional, shooting out in narrow jets at nearly the speed of light. If you're in the path of the jet, you're exposed to an incredible amount of radiation. If you're not in the path, you might not even know the burst happened. Here's the terrifying part. A gamma-ray burst from a relatively nearby star, say within a few thousand light years, could cause a mass extinction event on Earth if the jet pointed at us. The gamma rays would strip away our ozone layer, exposing the surface to deadly solar ultraviolet radiation. The burst would also create nitrogen dioxide in the atmosphere, causing a brown smog that would block sunlight and potentially trigger an ice age. And the source of this catastrophe could be a neutron star or black hole, just 20 kilometers across, thousands of light years away. Some scientists believe that the Ordovician mass extinction event 440 million years ago, which killed about 85% of marine species, might have been caused by a gamma-ray burst. We have no way to predict when or where the next burst aimed at Earth might come from. It could be tomorrow. It could be in a billion years. We wouldn't see it coming because it travels at the speed of light. The light from the burst and the deadly radiation would arrive at the same time. Magnetar flares are similar, but usually less energetic than gamma-ray bursts. However, because magnetars can exist closer to us than the typical sources of gamma-ray bursts, a nearby magnetar flare could still be devastating. The 2004 flare I mentioned earlier was detected by dozens of satellites and temporarily blinded most gamma-ray instruments in space. The wave of radiation was so intense it ionized atoms in Earth's upper atmosphere, causing the ionosphere to swell. If that magnetar had been just 100 light years away instead of 50,000, the effects on Earth could have been catastrophic. Now let's consider something even smaller, but potentially devastating. Strangelets. These are hypothetical particles of strange matter, a different form of nuclear matter where strange quarks are mixed with up and down quarks. Normal matter contains only up and down quarks. Strange matter might be more stable than normal matter. If strangelets exist, and if they're more stable than normal matter, they could convert normal matter into strange matter on contact, similar to Ice 9 in Kurt Vonnegut's novel Cat's Cradle. A strangelet could be microscopic, smaller than an atom, but if it touched the Earth, it could theoretically convert the entire planet into a strange matter object over time. This is highly speculative and most physicists consider it extremely unlikely, but the fact that we can't completely rule it out is unsettling. Strangelets might be created in neutron star collisions or in high-energy particle collisions. Every time we run experiments in particle accelerators, there's a tiny chance we could create something that converts all normal matter in its vicinity into strange matter. Quantum black holes are another theoretical tiny danger. If extra dimensions exist as some string theories predict, it might be possible to create microscopic black holes in particle accelerators or through cosmic ray collisions in the upper atmosphere. These quantum black holes would be incredibly small and would evaporate almost instantly through Hawking radiation, but during their brief existence, they would be incredibly dense objects with extreme gravitational fields in their immediate vicinity. Let's talk about vacuum decay, one of the most existentially terrifying concepts in physics. Our universe might not be in its lowest energy state. We might exist in what's called a false vacuum, a metastable state that could decay to a true vacuum. If this happened, a bubble of true vacuum could form, possibly triggered by a quantum fluctuation or a high-energy particle collision. This bubble would expand at the speed of light, and inside it, the laws of physics as we know them might be completely different. Atoms might not hold together. Chemistry might not work. Life would be impossible. The bubble wall itself would be the destroyer of worlds, and it could be triggered by something as small as a single particle in the right conditions. Once started, it would be absolutely unstoppable and undetectable until it arrived. Because it expands at light speed, we would have no warning. The universe as we know it would simply cease to exist, replaced by something else entirely, and the trigger could be something infinitesimally small happening anywhere in the observable universe. Rogue planets present another interesting danger. These are planets that have been ejected from their solar systems and now drift through interstellar space. A rogue planet doesn't have to be massive to cause problems. If a Mars-sized rogue planet passed through our solar system, even if it didn't hit Earth directly, its gravitational influence could perturb the orbits of planets, send asteroids from the asteroid belt into the inner solar system, or disturb the Oort cloud, sending a shower of comets our way. The planet itself might be just a few thousand kilometers across, far smaller than Jupiter, but its passage could spell doom for life on Earth.